The next speaker is Konrad Steffen. Conny is a director of the Swiss Federal Institute for Forest, Snow and Landscape. He's also professor in ATH in Zurich and EPFL in Lausanne. He's launching this Swiss Polar Institute, which is a brand new initiative. But above all, he's a witness. He's a scientist that goes every year since many years into the Arctic. And we never met each other before. I mean, I don't know why. I mean, we are working quite closely in slightly different fields, but we have many common friends. And when I told someone, "Do you know Conny Steffen?" The answer is yes. I met him in Barrow. Yes, I met him in North Grip. Yes, I met him in Station North. He's always somewhere in Greenland or in the Arctic. So he's basically a witness, as I told you, and he will speak about how ice is melting and what the consequence it will have on future climate. Thank you.
Thank you very much, Carlo. And it's actually nice to meet you finally. I have heard about you too, but I'm not going into detail now. It actually is an amazing place. I've never given a talk in such a beautiful room, and I hope it is inspiring not only our presentation but also our discussions. For the past 40 years I have gone to the Arctic every year. So I started in '76 as a grad student, and I got hooked and continued to went there. And I want to give you a brief insight what is happening with Greenland, with the Greenland ice sheet. We are monitoring the Greenland for the last 25 years with 18 stations continuously, and I want to show you what is the feedback to the current warming and how important is actually the acceleration of the melting. You see typically here a surface of the Greenland ice sheet with melt rivers, because the water is flowing on the surface for a few hundred meters, then collecting in lakes, and then penetrates through the ice, and I want to talk to that in particular. So let's look at Greenland. It's actually the biggest island on the Earth. It extends 2,500 kilometers from north to south, about 500 kilometers east to west, and it has an ice sheet on top of it that's 3.3 kilometers thick. If you actually melt all the ice and put it into the ocean, and with our current warming that will happen over a longer time period, global sea level will rise by 6 meters globally. All the coastlines. Don't want to scare you about Venice. It's not happening tomorrow. But if you look on the long term, unfortunately, there is a prediction that most of Greenland might melt in a few thousand years. If you look in the center, that's what Andrea mentioned as well. This is the sea ice, and the sea ice is retreating very fast. Sea ice is only 1 to 2 meters thick. Sea ice is there to insulate the ocean, that during the winter we do not lose all the ocean heat. So this is an insulator, but even an insulator disappears during the cold period because you don't have cold enough temperatures to maintain the ice at the surface, and that has a very strong feedback, similar to that what Andrea mentioned. I will summarize the warming quickly in a few decades. And when we look at warming, and I'm a climatologist as well, we look at 10-year means over a long time period. So we take a 30-year mean, and here we were taking a mean 51 to 1980. We compare from the 70s. You can see hardly any warming or change. The color is white, or it's in that 0.1 range. I jump to the 80s. We can see some warming in the northern latitudes, in the peninsula and in the Antarctica. If we go now 2000, 2010, it has changed significantly. That is actually the signal what we see, the imprint of our greenhouse gas warming. And the last 4 years, that's only 4 years, were even stronger. We have warming patterns in the polar regions and down to mid-latitudes of 1 to 2.5 degrees. Last year was the warmest year ever measured, and you can see here this is only the annual 2016 compared to a different time period, 80 to 210. So I took a warmer time period. If I would have taken the old one, it's even stronger. And it actually displays very well what Andrea also mentioned, that is the albedo feedback in polar regions, but also in alpine regions. I will actually include some of the Alps, because the Alps is the third pole, and it's happening exactly the same than in polar regions. We have a 2 to 3 time amplification of the mean increase in temperature. Why do we care? Obviously there is a reason behind it, because if you increase air temperature, you start to melt ice. That's shown over here. And we are currently melting glaciers, ice sheets at the rate of about 3.4 millimeters per year sea level rise globally. So every year, almost half a centimeter, the ocean is higher, just because of the melting. It's not only the melting that makes sea level change, also a warmer ocean temperature. If you have a warming of the ocean, what is currently happening, the ocean has a bigger volume when the temperature increases. So about a third of the global sea level signal today is simply because of the warming of the global ocean. Then we have height changes, but I won't go into that detail. How do we know all that? We have several ways to measure it. If I go to the old period, and I will mention that these are the tide gauges, to attach an instrument that swims in the ocean, and then it records the height. And that has been done since 1700 to present. So we have quite a long time period. The only problem is you have to know this piece of land has to be solid. It has to stay at the same height. It's not always the case. Sometimes the Earth is moving as well. Our more modern instruments, and I have lived in the US for 25 years. I worked with NASA a long time, developed satellites with them. And we use satellites that have a laser here, it is green, and it actually measures the distance very accurately from the spacecraft to the surface. And if the ice cube is melting, we can detect within a few millimeters the height change from one satellite orbit to the next. And like that, we can very accurately measure the height change of ice sheets or the height change of the ocean. It's shown over here. This is his radar. I will not go into detail. This is the gravity satellite, also a unique instrument that we can look at the mass, not just at the surface height change. Let's go into the back time, to the last warm period, 120,000 years ago, 30,000 years ago. We had a time period that was about 2 degrees warmer than today. That is the time, the temperature increase we are allowing our Earth system to adapt by 2100, 2-degree warming globally. During that time, we had a sea level that was 2 meters higher than today. The only problem, of course, is it had a long time to adjust. You can see these are 10,000 years. So over a long time, we are able to melt out some of the ice. So when we have a 2-degree warming, we would not expect a 2-meter sea level rise, but something maybe close to that. Over the time, we had quite a variable sea level. That was the last glaciation. Just 10,000 years ago, sea level was about 130, 40 meters lower than today. That's where we had the mass migration coming from Asia into Northern America. And again, what was shown by Andrea very nicely, with temperature, I show the same, about a stable sea level during the last 4,000 years when civilization developed. We had no sea level change, and this will have a change here in a warming climate. We expect quite a change. That summarizes it, all the measurements we actually have from 1700 to present. These are the floating instruments in the ocean. This is the time period we have very accurate satellite measurements. So earlier we had a sea level increase of 1.7 millimeters per year, which was an adjustment from the last ice age. Currently we have a sea level change of 3.3 millimeter. You can see the uncertainty is small, so these measurements are quite accurate, these are global. The question is, where is it going? This is the prediction. And I was a lead author in the IPCC, the Intergovernmental Panel for Climate Change report, and we summarize from all the models that we expect a mean sea level change of 1 meter by 2100 with an uncertainty of 80 to 120. This was 2013. I don't want to scare you, but the more latest reports, more latest papers that include ice dynamics more accurately, and I hope we hear more from our speaker in the after me, it might be up here. But I would say there is a large uncertainty. There are a lot of processes we are not understanding very well, but that sea level is increasing. We are quite certain because we do have the accurate measurements now. What does it mean 1 meter? If you just look to Northern Europe, you can see 1 meter as a mean will actually reduce living in the area where you have red color, because that will be underwater. I'm quite sure Europe will be able to adjust for any change because we have mitigation, we have probably investment possible to do it. If you go to Asia, if you go to Bangladesh, if you go to other places, they have not the means, and the current estimate is with 1 meter sea level increase, there will be a migration of 150 million people. They have to move away from the area. If you go for 2 meters sea level rise, they actually estimate 450 million people. And we all know how poorly we do with immigration today. If you now talk about millions, it is something we should address today, and we shouldn't wait for another few decades before it's too late. I mentioned Greenland has approximately 6 meters sea level rise, potentially. Greenland is, according to the last estimate, if it loses ice at the current rate, it still survives for roughly 7,000 years. Unfortunately, sea level, the melting is faster than a linear curve, so I come back to that. It's actually accelerating. When we go to Antarctica, because this is the big brother, but it's a sleeping big brother that is starting to awaken. And I come at the end of my talk to it, taking in the entire ice volume from Antarctica, which is up to 4.5 kilometers thick, and you would melt it, which is not happening, has not happened for 1 million of years. But the volume of Antarctic ice for sea level equivalent is 60 meters, 60. So you add Greenland and Antarctica, you will change, of course, the coastline. It's not happening in short time, but there are possible instabilities I will discuss quickly, and that's where we have a big uncertainty. That is actually something we should show to Trump if he doesn't believe. That's where the waterline will be at the Statue of Liberty. Maybe they have to get a new one from France. Let's make a very quick assessment. What does it actually mean, mass balance? Because we all talk about, is Greenland in balance? Is it losing mass? It's a very simple graph and a very simple equation. Input is precipitation. It's rain or snow. You can see up here in the order of 600 gigatons or cubic kilometers. When you look at what we are losing is melt, or where the ice breaks off into the ocean. These two numbers, this is roughly 300, this is roughly 400. We have some evaporation where we actually lose snow into the atmosphere by vapor. If you take input minus runoff, minus discharge, minus evaporation, you will see, but I'm losing it here because the screen is not big enough. It's a negative number, and the number is in the order of 50 to 200 gigatons. That was the mean for the last decade. If you take the more recent data for the last 5 years, currently we are at 350 gigatons ice loss in Greenland every year. Is that a lot? If you take all the ice you have in the Alps, all the glaciers together, we have 60 gigatons of ice in the Alps. That means we are losing every year 6 times all the volume of the glaciers what we have in European Alps into the ocean. which is exactly 1 millimeter sea level rise. Let me quickly summarize what we actually measure on the ice. I mentioned I have been there for a number of years. I started the camp around 1990 on the ice sheet, and you can see it's quite variable. These are all the stations. We make measurements for 25 years continuously. It measures every few seconds, every hour. All the data is transmitted via satellite link. And when we look at the temperature increase, this is the annual temperature for what we call Swiss camp. It's a camp at 1100 meters. It was built at the equilibrium altitude. That means in the summer, the snow melted, that fell during the winter time. And I went too fast. If I take the mean, I'm not going into variability here. This latest number is up here. We have an increase that is quite significant for a measurement on the ice sheet. That means we are measuring on ice, it's not on land. And on ice, the temperature cannot go to 10 degrees. It stays close to the melting during the summer. Still, we measure about 1.5 degrees per decade. Over the 25 years, it's roughly 2 to 3 degrees just on the ice sheet. What is more important, and that goes back to Andreas' point, albedo, which is the reflectivity of the short wave radiation, the sun. You all know when you go skiing, you need very good sunglasses because the snow reflects. As soon as the snow gets wet or the snow disappears and you have just ice with water, the albedo reduces here from roughly 80%. These are the years, these are the months. You can see in the summer, this bullseye grows. That means we get darker and darker surfaces. The energy from the sun stays on the ice sheet and absorbs, that means melts the ice. So it's a very strong feedback, and that drives actually the warming in polar regions, or amplifies it by factor 2 to 3. This is the example I use most, which is the long-term measurements of the Swiss camp. If Greenland would be in balance, that means input minus output is 0, we would be along this line. Whatever the snow falls, it melts in the summer. You can see after 2000, this curve drops down. And over the period from 2000 to present, we lost 12 meters of ice. That's 1.5 times the height of this room. And I can illustrate that with my graphs here, because that's where the first time we lost our station, or mainly part of it. This is the most important part, because that was the sauna. So there was no longer having a sauna after a long day. But since we had very good students, we rebuilt the station, and you can see it actually was built on the same legs, big platform, but we didn't know it's going down the drain. So the following year, there was no help. It was really gone. We had to rebuild it. We rebuilt a new station, level to the ground. This is a big wooden platform, and you have beams going down about 12 meters into the ice. And we expected, of course, now that's it. We have time to work, do the science. We came back the following year, that means back here, and we actually found the station a bit elevated. That means another 2.5 meters of ice disappeared. And that's within one season. And the last time, luckily, this has been actually slightly leveling out, otherwise I would plan another station. Given that fact, Swiss Camp is on sale now. Whoever wants to buy it for $1, I'm giving it away. Because we have to build a new station further up. It's no longer sustainable, I would say. I was back last year because we finished the movie with Al Gore. You can't see him, but he's standing here. It is now 4.5 meters above the surface, and we have a swimming pool underneath. I mean, it's really a cheap station. You get $1, a swimming pool, and all the hardware. So make me the offer. I start at 1 Swiss francs. I think dollar is no longer. I have one bidder, Andrea. Good. Okay. We can put animations together how much of Greenland melts every year. There are satellites. Of course, we use satellites because the point measurements are there to explain the satellite, to calibrate. And that is you see the year moving, and the waning, that means the melting of the ice sheet. I skipped it because I don't want to go through the whole time series, but I show you the result from 79 close to present. This is the variability we can explain because of the ocean circulation. But in total, we increased the melt area, which is the red color here for 2007, but it goes along here, by 65%. So only within 30, 40 years, the amount of melt from area increased that much. And if you increase that much melt, it has some effect on the ice. And that's what I want to discuss in the following. The summary from ESA, the European Space Agency, that actually shows the impact of Greenland lowering. You can see here in the red color, this is all surface lowering. A little bit elevation, because in a warmer climate we expect more precipitation, so the high area of Greenland has slightly increased, a few centimeters, but the low areas have decreased significantly here on an annual basis, and they do the same. They plot the sea level contribution for Greenland over the time period 2092 to 12. That was the same curve we used. We used the same data to actually produce our IPCC figure, and you can see in there around 2000 it started to actually increase. We had close to a balance. This is not our measurements, this is the summary of all the publications we could find talking about mass change for Greenland, and then that gives an uncertainty, and you can see the contribution just within these 12 years was already close to 1 centimeter sea level change. And it is not a straight line. You can see how this is bending up. And that's the big question. How quickly is it accelerating? We don't know, but we have good modelers, and I hope they give us some insight into it. The last part, I will quickly look at the surface. When you stare down on Greenland, you can see the outline of the ice sheet. This is Jakobshavn-Isbrae, a very fast glacier. And you can see these blue dots. These are lakes. And if you look a bit closer, these lakes actually collect the surface melt. And the lakes are a few kilometers across, only 10, 20 meters deep. But the surface in Greenland is undulated because it reflects the underground. There are big mountain ranges under Greenland, and it's a standing wave. So you keep that surface undulation. And if you stare down on these lakes, they suddenly disappear. It's not that you have a big river running towards the coast. The water collects and disappears, and I can show that in closer. Oops, I'm going too fast here. That is the lake, one of the lakes. The water, you can see it's all running into the center. That's the lowest point. The water is running out here and then disappears outside the screen. The screen is too short here. It has a hole here. What happens is it's a moulin. It's called moulin in the French word, a mill. So it actually carves its way into the ice. The ice is 1,000 meters thick here. It goes 1,000 meters through the glacier and then lubricates underneath the ice sheet. And that is the phenomena, what we call the lubrication effect. We actually put up stations. These are GPS stations that measure velocity of the ice sheet very well, very accurately, to a centimeter accuracy for over 10 years. And like that, we are able to show that in the summer month, this is the mean speed of the ice sheet. The Greenland ice sheet accelerates up to twice the speed. This is 30 centimeters per day at that location. And then I have 3 minutes left. Okay. Good. And then you see, oops, I can summarize that actually in this movie. No, I don't. I move back forward into the moulins. We actually wanted to understand what is the mechanism of these moulins that actually drain the water through. And unfortunately, none of my grad students volunteered to go straight down here. It's only 100 meters, then it's horizontal, and then another few hundred meters. So we designed instruments to actually make these measurements. And the instruments were lasers that are rotating. I only show you the result of those. And if you look into a moulin, which is hard to see with this lightning, this is about 10 meters across. It's a big opening, the water streams in. It's 100 meters down, and then it continues at several levels. We were able to actually show the volume of that moulin by this laser, by lowering it down. The important part is you had inputs at different levels. So the water comes in at 20, 40, 60. So this is actually a tube that collects all the underground rivers. And that actually pushes the water underneath the ice sheet. Water is heavier than ice. So you can lift up the ice and reduce the friction. So it's moving faster towards the coast. More melt means fast moving ice, and about 50% of the signal today is actually the ice loss in the summer months. In the winter it's back to the normal speed. We had an interesting project. We haven't succeeded yet. We want to go through the moulins straight down and walk out underneath the Greenland ice sheet. So I'm still looking for very brave ice climbers. I found already a few, but the project is on when there is no running water. This was just a test together with the Red Bull ice team. They wanted to see the opportunity. For us, scientifically, it's more important. How is the temperature changing? Because if you have more of these moulins, you actually warm up the entire ice sheet, and that flows much faster. I don't see any volunteers either, so I move on. And I think I want to jump over this. This is an important view graph that shows Antarctica. I only will show Antarctica and one glacier. Antarctica is not melting at the surface, it's too cold. Antarctica is melting from the ocean here. This is the extent of the Antarctic ice sheet. This is the ocean temperature that has increased +1 degree, so it is warmer than freezing. If you look over here, the ocean all along here is at -1.5 degrees, so it's at the freezing point, it's not melting. In West Antarctica, and this is new, the ocean actually melts along this coast, which is several kilometers thick, because the glacier sits on the underside of the ocean. And that's where we have a very similar ice loss than the Greenland ice sheet. And that is accelerating, that can be unstable. I don't have to go in detail, but it becomes a major contributor for sea level change in the future years. Today it is already 100 gigaton. Let me jump to the glaciers, because it is important to actually also mention we don't have simply, and I put Mortrach Glacier in because of our discussion, so I found an example. This is only 85 to 2007. So 85 you had a big healthy tongue here. 2007 it's here. Right now it's sitting above here. Same, I can give you that graph. It's the Gries Glacier. You can see the extent 2003. So 2016, the tongue has gone all the way back. My final slide actually summarizes the Rhone Glacier. You don't need to look in detail. That's the little ice age that was in the 60s. That's where we expect it in 2100. My summary is about 50% of all the glaciers will disappear in the Alps by 2100. This is the summary slide. This is the sea level contribution from Antarctica. This is the one from Greenland, based on all the literature. This is the sea level contribution from the glaciers. It's way higher than just Antarctica. It's the same than Antarctica or Greenland. The unfortunate message is there is only 40 centimeter sea level rise left from glaciers. We don't have more ice. So if you neglect those, we have to concentrate on these two that still currently the global sea level increase is by 50% ice contributions from the glaciers. I'm out of time, I think, because otherwise we don't have any lunch. Thank you very much.
Thank you very much. We have time for one quick question. Anybody? Curiosity over there.
Thank you. Thank you for the interesting presentations this morning. My question, I don't mean to sound like a climate skeptic, but it goes back to both of you. In all these projections and the results that we see so far, is there a way to sort of decouple how much of climate variability, the change in the climate variability, is playing a role in sort of amplifying the effect both in the Arctic and the Antarctic ice melting? So is there a real amplification in the climate variability itself that can also speed up this process, and if there's a scientific way to sort of decouple that from the estimates? Thank you.
My answer is actually, we looked at that in a lot of detail, and we run a lot of climate models, and I'm not the expert on the climate models, but that was part of the study, that if you run the climate models without any greenhouse gas, no CO2, no methane, no dust, etc., you could not show the increase in temperature we currently see. If you add methane, greenhouse gas, also CO2, and other greenhouse gases, it matches the temperature increase very accurately. That doesn't answer your question how much of the variability is. We have a variability which is decadal, and that one is like an ouverture, an overlaying long-term variability. In there we actually understand some of it, but not all. If you look on the longer term, I would say 90% is greenhouse gas. 10% is unexplained. Doesn't mean it's not coupled to a recoupling we don't understand, but it's not a big other process. So the greenhouse gases are dominating the current warming.